Hi, greeting for Total Fidaos. My name is Lim Tian En, and together with my friends Yap Ka Heng, we will present about the chemical force microscopy, which is under one of the categories under the scanning probe microscopy. So basically, the chemical force microscopy is same as atomic force microscopy. The operation way is almost the same. Is by scanning the substrate surface using the tip, like the figure over this side. The chemical force microscopy is just difference at the tips. The tips has been modified, the chemically modified with specific expo functional group. It can be just such as CH3 or COH, and it depends on the specific function you want to carry out in a system. And the main purpose of the chemical force microscopy is to provide sensitive resource to measure and map the surface chemistry information. And from that, from the information, you can quantify the adhesive or repulsive force associated to inorganic materials and biological samples. And throughout the control of chemical interaction between the AFN tip and the sample. So basically, these are the few of the examples of the applications that the chemical force microscopy CFM has been used. Example is biological science, nano biosensor, and mechanical sensor. There are still a lot of them. There are just a few of the samples. Okay, so I think that my friend Yap will continue with the operating principle.
Greeting to Dr. Fidel. So I'm Kaheng. So right now I'm going to present the chemical force microscopy working principles. Okay, firstly we need to take a look the schematic drawing of the chemical force microscopy setup. Firstly we need to know we have the adhesion force here and then the friction over here. And what is the adhesion force about? Adhesion force is the attractive force between the molecule. So we call this attraction force as adhesion force. Okay, then firstly, this chemical force microscopy consists of an integrated cantilever tip assembly, which can interacting with the samples. Normally, is biological the sample surface. So the integrator cantilever tip is over here. And then next we have a detector that measure the displacement of the cantilever. So we know there is a displacement of the cantilever and the sample over here. So the detector will detect how much is the displacement over here. Then we do have the feedback electronics to maintain a constant image parameter such as tip sample separations of force. So between the tips and the sample, we can detect the forces and then we can generate the signal to the electronics and the electronic will give a feedback to our system. And lastly, we do have the vertical displacement due to the normal forces and the lateral twist due to the reflection of the cantilever. Measure using a quadrant for the diode as shown in figure on the left. So we have a quadrant for the diode is here. So we can accept the signal uh, due to the lateral forces due to the friction of the cantilever and also the normal forces. So we can take the signal and then go to the photodiode. Alright, so we need to understand the working process in the CFM that we have just now. So firstly, we need to uh, give a samples biological sample based on the piezoelectric XYZ translator. So we put the sample over here, and we have the three vectors XYZ. And then we have a laser beam is reflected from the backside of the tip onto a photodiode to measure two types of tip surface interaction. So we have a laser over here. Alright, so it's reflect to the backside of the tip onto a photodiode. Right, this is a laser. There the laser is to measure two types of tip surface interaction. So we have adhesion forces and also the friction forces. So we need to measure these two. And then when the sample approach touches and is withdrawn from the tip, so the tip is here, the little triangle over here, the tip will move up and down in response to the surface normal force Fz, resulting the vertical deflection signal Vz. So the tip will move up, move down, so that we can uh, react to the surface normal force Fz, and then once we get a normal forces Fz, we can obtain the vertical deflection signal Vz as well. And then not only the tip will move up and move down, but also the cantilever will also twist in response to friction force to the Fx. Okay, using the lateral deflection signal Vx. So other than move up, move down, the tip also can move x in x direction, so that we can get the friction force. And then once we get the friction force, we also can get a signal Vx. And lastly, the insect illustrates the chemical specific interaction between a AU-coated SCS3 terminated tip contacting a COOH terminated region of a sample. So we take a look over here. Okay, so we have a CS3 over here on the top, and then we have the COOH over here. So we can from there, from the CFM, we can study the interaction of the CS3 and the COOH. And then we can adjust the parameter of the CFM as well. So the force values are determined from the normal displacement, delta Z, or tilt angle, delta delta angle of the cantilever from its resting position. So we can adjust the normal displacement, whether we want to make it further away from the sample or nearer to the sample, or we can adjust the angle of the incident laser, whether we are going to put it here or put it here, right? So and then the CFN can in principle measure a molecular interaction ranging from a weak van der Waals, which is less than 10 power of negative 12 Newton, to a strong covalent 10 power of negative 7 Newtons bond. And then ideally, if you want to measure with the CFM, make sure we are conducted in a vacuum. If perhaps we can use the ultra vacuum environment. If the measurement are conducted in ambient air or liquid, the thermal noise are significant. So for example, if we use the vacuum, okay, if we use the vacuum, so the quality factors, wow, will be in between 1,000 and 100,000, which is a very high quality image, so it very less noise that we have. But if we use in ambient air or liquid, the quality factors will drop to 10 to 100 only. So we will get a lot of noise from it. So we want to get a very clear and very perfect result. So you need to use the vacuum environment. So so now let us take a look the how if we do the CFM in three types of situations or three types of environment. First we have the vacuum, and then liquid, and also the ambient air. So we will take a look at the comparison between the force measurement in these three types of scenario. So the figure A show we conduct it under the ultra high vacuum, and the B is under the liquid, and the C is the ambient air. So let's take a look at A first. In the figure A, the interaction under the high vacuum condition are determined by the solid surface free energy. So in ultra high vacuum, we don't have other particles. So we just only have the the tips and also the sample. So the so the interaction is just is predominant by the solid surface free energy. So only the surface and the tip. So next we take a look if what if we conducted in a liquid. So pulling apart the surface and the liquid will result in their solvations upon separation. The magnetic of the adhesive force is defined by the solid liquid surface and free energy. So if you take a look at the figure B, what is the difference between A and B is we have the liquid particle here. So we pull out the tips from the samples? What happen next is the liquid particle will go inside here, but is no stick to the tip and the sample. It just liquid particle only, but is already go inside it. And the adhesion forces is defined by the solid and the liquid surface free energy. So let us recall back what is the adhesion force is the attraction force in different types of molecules. So we call it adhesion force. So we have the solid here and the liquid particle here. So it's two different types particles. So it's called adhesion force. And then C. So what is the difference uh, between figure C and figure B? And we can see that the the water molecule is stick to the tip and also the sample, but figure B no, doesn't have. So the experiment conducted under the ambient condition reflect wettability of the surface, since the product-demand interaction is the result of capillary forces. So first we have to understand what is capillary forces. So a capillary forces is when a scenario or the situations the adhesion force is greater than the cohesion force. So adhesion force we already know is the attraction force between two different types of molecule, and the cohesion force is attractive force between the same type of molecule. So if the cohesion force is greater than the adhesion force is greater than the cohesion force, will result in a capillary force, which means we will result in the wettability of the surface, which means the water particle will stick to the sample and also the tips. Alright, so let us look into some of the CFM image examples. So we can see that we have two figures, figure A and figure B, both in the 100 micrometer times 100 micrometers. Okay. Then the lateral force image of a sample pattern with a region uh, terminating in CS3 and COH functional groups recorded in water, and also air with metal functionalized tips. So for A, the light regions are areas of the high friction and correspond to the first surface region terminating in CS3 functionally, and in dark regions represent the low frictions and correspond to the surface areas terminating in COH functional group. So this is what the figure A. And for the light regions here, it show that is high frictions and terminating the CS3 functionality, and that region over here is the low friction forces and terminating the COH functional group. In B, we have another case. In B, same things. The high friction represent the light. The right area is representing the high friction. But here is terminating the COH. So it's totally different with the water example, which is the light region is terminating CH3, but in A with fractionalized tip is terminating the COH. So in B, figure B, the dark region is representing the low friction as well, but is to terminating the CH3 region.
Okay, so let me continue with the calibration of the chemical force CFM. So basically, there are two common methods. The method one is parallel scan, and the method two will be like perpendicular scan. And this is the figure showing the method one. So basically, the method one is by starting by scanning parallel to the cantilever beams, and you will obtain a topography image forward and backward. So from if you can see from the diagram over here, the scanning is like parallel to it, so that the tips over here, the cantilever over here, and you can see the image will be directed to the like almost the middle of the photo detector. And in the way detecting this scanning parallel, there will be a force applied to the base of the cantilever to maintain a constant factor, and is directly related to the frictional force applied to the tip. And is it important that the calibration method is important for the value of the coefficient of the friction. The things that we want to get is this coefficient of frictions. So from here you can see that if the explanation that the given is that if the absolute value of the normal force applied to the cantilever is recorded at every point on the scan line, this can be combined with the length and height of the cantilever to produce the coefficient of frictions. So from here, the adhesive and interatomic force will actually it will affect this simple approach. So this will make a large uncertainty. So this method is not really reliable. So you will have uncertainty. And moving on to the second method, the perpendicular scan. So what is so different is that you can see the cantilever over here is what is different from the method one is that you can see that the cantilever over the image here is twisted, and you see the image directed is not at the center anymore. So the step is basically over here, the lateral bending of the cantilever during perpendicular scan, like this twisted. Okay, so you will get a shifted photo detector, and over here you can see that the explanation said that the friction is not the only factor contributing to the fracture of the cantilever. Okay, so basically the most important part is that you can see that the average value produced much more reliable value for the coefficient of friction compared to the first method. So this is basically the two methods they are using to calibrate. One is parallel scan, one is perpendicular scan. Okay, so let's moving on and see that the parameters that will cause the signal will cause noise to the signal and affect the result. The first parameter will be the quality and condition of the probe. The quality and condition of the probe is important that since that if low quality tips are used, it may lead to artifact in the image and cause incorrect result. And this artifact is basically the mistake that you have done during the preparation of the experiment, and it caused the uh, result become not so accurate. And after using it, be sure that the probe are gently dry in steam of inner gas and store under the same gas in a desiccator to avoid high humidity, so that the oxidation of the probe will not happen. The second will be the material of the probe made of. The material is important and it depends on your choice of the material of the probe. If you choose a suitable probe, you will get a better result. And it can be seen in terms of uh, tip radius, spin constants, resonance frequency. Uh, so by choosing the correct probe, you can free of inaccuracies due to the stiffness of the cantilever, the tip radius, strip, sip, and its dilation in CFM measurement. So you need to know that actually the tips may have impurities such as dust or other substance that stick on the probe from the previous experiment. So unclean probe can literally lead to contamination of the materials. So actually pre-cleaning is an important step to make the probe under good conditions, and it should be carried out in high vacuum chamber. And you need to identify the substance, molecule, or reagent of the materials. By doing so, actually you are allowed the potential reaction and binding, eventually the complete molecular architectures to functionalize the tip to be predicted. And this is important as the CMS is used to measure the adherence and force. So the condition of the chamber, you need to clean the chamber with inner gas before using. This is because that before the experiment, before you doing the experiment, they may have some substance that live in the chamber, and this will affect your result. Okay, moving on to the advantage and disadvantage of CFN. So basically the advantage and disadvantage are listed here. The advantage are like simple sample preparation. You don't need complex sample preparation. And it will give you a very high resonance up to atomic size resonance. And for CSM, it is work in vacuum, air, and liquid. And living system can be studied such as imagine adherent cells. These are all the advantage of CFM. The advantage are like limited vertical magnification range. You need to know that actually the things you are measuring are in a very small size only, so it's limited. And this is one of the important thing also. When the substance that deposit on the surface of the material are not deposited completely, it will affect, it will make the image uh not not nice, and it cannot image the materials. And the tips and the sample are very important, since that the data will be depending on the tips and sample. If the tip or sample are damaged, the data will not be reliable. Okay, I think that's all from us. Thank you.